Hi, this is an introduction to logic. I'm Mark Thorsby, and this course overviews the basics of categorical, propositional, and predicate logic. Today we're looking at predicate logic, and we'll be looking at how to use the rules of inference within predicate logic. In particular, we'll be introducing the basic rules of universal generalization, universal instantiation, existential instantiation, and existential generalization. But before we get into all of that, let's sort of start off with a brief review of what we looked at in our first lesson, right? The first thing we looked at in terms of translation, right? And it's similar to propositional logic, but different, is that when we have a basic statement, for instance, the grass is yellow, we translate this by taking the predicate and capitalizing it, and then taking the subject and making it lowercase and putting it right afterwards. So we get YG. But similar to propositional logic, this symbol here, capital Y, lowercase g, stands in for the entire proposition. Now, although I'm not going to go through the proof and the reasoning to why this works, what it ultimately means is that when we begin to symbolize this, we add a couple rules. This allows us to combine the best of propositional logic with categorical logic, meaning that we can actually we can actually analyze and give proofs for argument sequences that contain categorical claims like all dogs are mammals and things like that. Whereas propositional logic didn't have that capacity to do, right? Now, one of the things we talked about, though, is that this is how you symbolize a basic proposition, but when you symbolize categorical claims in proposition, you need quantifiers, right? And there's two types of quantifiers. There's a universal quantifier, and that looks like an x with fx, right? Where f stands for any sort of propositional, and this is actually referred to here as a statement function. There's universals, and there's also existential quantifiers, or if you will, particular quantifiers, and this is symbolized with a backwards looking e and an x, and then fx, and this is a existential statement function. Okay, that's what we looked at last time, and really what I wanted to do is practice translating and understanding how these things work. But one of the last things I said in the very end of my last video last time is I said that the rules of implication, the rules of inference actually work, right? So let me give you an example here. Right, the rules that we discovered in natural deduction still work. So let's imagine I had this problem, right? X of fx, then x of tx, and my second premise here was x of fx, right? I could utilize modus ponens in this problem, right? Because this thing is my p, and this is my q, right? P then q, and this here is my p. And the modus ponens rule says if you have p then q, and you do have p in fact, you can conclude q. So line 3, I could conclude this thing, which would be x of tx, okay? So I could use modus ponens in this case, right? But we're going to see there's a problem here, right? There's a problem here. Is what if I had a problem that looks very, very similar? What if I have x, but instead my fx and my tx are both bound to that universal quantifier, right? Because remember, the quantifier will always refer to whatever follows immediate afterwards, and the premises here mean that this whole thing is being quantified, right? And let's imagine I have x of fx, right? Notice here that these would be two different variables. This would be a p and an r, if you will, which means that you cannot use modus ponens here. I can't utilize modus ponens here. I have to break apart these two things, right? Because the modus ponens rule says that there's a conditional between two different propositions, right? And this is just one proposition bound by a quantifier, so I can't utilize modus ponens here, which means that the rules of implication and the rules of inference that we looked at in terms of natural deduction have a severe limitation. So what are we doing in this video? In this video, we're going to add to our tool set, and we're going to add 4 new rules or tools that allow us to ultimately in order to solve these sorts of problems. Excuse me. Okay, 4 new rules. Now, these 4 new rules are going to consist in terms of basically, in the one hand, we need to either, let me erase that, we need to either generalize or instantiate quantifiers. Okay, now that means that we're going to actually, the first rule we're going to look at, well, not in this order, but the 4 rules are going to look like this. You can have a universal generalization or an existential generalization, as well as a universal instantiation or a existential instantiation. Now, what does the generalization allow us to do? The generalization allows us to go from a non-categorical claim into a categorical claim. Or in other words, it would allow us, if we just had fx, to go to x of fx. Okay? Now, the existential generalization does the same thing, where we begin with a non-categorical claim and we move it into an existential categorical claim. Okay. Now, instantiation does the reverse. Instead of moving from a non-categorical claim to a categorical claim, instantiation allows us to go from a categorical claim into a non-categorical claim. Or in other words, it allows us to remove, maybe this would be easier, right? When you generalize, you're basically going to add a quantifier. And when you instantiate, you're going to remove the quantifier. Right? So you can see here, for instance, in this problem, right? In this problem, I actually need to remove this quantifier. I actually need to remove both of these quantifiers in order to solve the problem. And if I wanted to get x of tx, I would then have to add the quantifier on the back end. If my conclusion was supposed to be x of tx, I need to first instantiate and then generalize back to this. And you're going to get a handle on this as we go through this. So what I want to do here is I'm going to move slowly, and I'm going to start with the universal instantiation because, like this problem, we have to begin by instantiating and then generalizing. And most of the time, that's what's going to happen, okay? So let's start off here with our first rule, right? Our first rule here is universal instantiation. And when we do a proof sequence, we're going to just write UI here to give us the example. Okay. Now, I think the best way for me to do this is actually write the actual rules. So the universal instantiation says that if I have x of fx, right, where here this stands for any statement function that is bound by a universal, right? I can always, and here we're sort of going downwards. If you start with this, you can always instantiate to fy, right? Now remember, x, y, and z, these are our variables that we can use, right? And they stand for anything in the universe, right? That's really what it means. And you know, take a look at my earlier video to help explain what this means in terms of language. But it means this. Anytime I have a bound variable, I can instantiate it, but I can use a variable when I do in the instantiation still. Okay? I can keep the variable. Here there's a y just to show that you can keep the variable, but it could be an x or a z or whatever. Right? Another thing you could do, though, possibly when you instantiate, is if you had x of fx, you can go from this into fa, okay? A here. And this is known as a constant, right? Namely because the a here refers to something actual. And here's the critical thing is that if I go from here to here, why is it that I'm allowed to do a constant here? I can switch it to a constant. Let's imagine that I said, for instance, all dogs are mammals, right? That's what this statement means. Roughly speaking, all dogs are mammals. Strictly speaking, we would write it a little bit differently, right? We would write anything in the universe, if it's an x, if that x is a dog, then that x is a mammal, right? That's what that essentially looks like, right? But this whole thing here is a statement function, so this is our fx, right? In relating to this definition here, right? Well, let's imagine if all dogs in the universe are mammals, well, what if I took an example, what if I wanted to demonstrate this claim by pointing to a specific dog? I can demonstrate the claim by talking about Spot, for instance, right? Now, the constants I can use only x, y, and z, so that means a through w I can use as constants, right? So if I did this, x to dx to mx, if I instantiate it, do a universal instantiation, I can demonstrate it with my particular dog, Spot, and it would look like this. We would cut out the the universal quantifier, and we would end up with this. ds, where s stands for Spot, to demonstrate the universal, right, to ms, okay? That's what an instantiated universal instantiation would look like, okay? Now, there's some important rules that we should mention, right? We'll put a little asterisk here. You cannot instantiate a negation. Why is that the case? You can't instantiate a negation because you can't show a demonstration of something that's not the case, right? You can't turn a nothing into a something, right? That doesn't make any sense, right? If I said there are no unicorns, I can't demonstrate that claim by talking about a particular unicorn, right? Right, because that's what we said the instantiation is. It's a demonstration of a particular, in this case, a Spot. It's a demonstration of a particular member of the fuller category, the dogs, in this case, Spot. Okay, so you can't instantiate a negation. That's an important feature, right? But that's what a universal instantiation looks like, okay? What I want to do here is just go through these fairly quickly with you. Well, maybe I'll do an example problem for each. Okay, so let me do an example problem. This problem is, I'm just going to read it to you. I'm not going to write it out, but it looks like this. All philosophers are speculators. Hegel is a philosopher. Therefore, Hegel is a speculator. So let me write out the problem of what that would look like, right? If there's an x in yours, if that x is a philosopher, then that x is a speculator, right? Hegel is a philosopher, right? Therefore, Hegel is a speculator, right? So let's imagine I had this problem here. How could I solve this problem? Well, I can use universal instantiation, okay? Now you can see here in universal instantiation, I can either instantiate to a constant or to a variable. What should I instantiate it to is the question. Well, oftentimes look to the conclusion, right? Notice that I have an h here in the conclusion, and I have a ph. It seems like I should probably instantiate to a constant, right? So you want to look to your conclusion to give you a clue in terms of whether or not you should instantiate to the variable or to the constant, okay? So number 3 here, I'm going to instantiate this. Now here's the trick. Something to remember. You can only instantiate the entire line here, okay? So that means we're going to instantiate this to ph, then sh. And the reason I chose h is because I'm looking for Hegel. Hegel's an example of a philosopher. He's a member of the fuller category, so I can instantiate to him. So that'd be line 1, universal instantiation. Now once I've instantiated it, now I can utilize modus ponens because I've unlocked this sequence from the statement function by removing that universal quantifier. So since I have this, I can conclude sh. That's lines 2 and 3 modus ponens. And now I can utilize my rules of inference or implication, okay? And that's how you would do that problem. That's a good example for you, right? Okay, so let's move here to the next one. That's universal instantiation. Let's now do a universal generalization. Oop, I guess I ran out of room down there. Okay. So this is number 2, universal generalization. And this is UG, okay? Now, remember, instantiation removes that quantifier. Generalization is going to add it back in, okay? So let me write down the definition the way I did last time. And that's going to look like this. For universal generation, if I have function y, I can generalize it to x of fx. Now remember, if I had fx, I could still utilize that. I don't have to change the variable. The only reason they're different here is so you can see that you have to generalize from a variable, because we're going to find out a rule here is what's not allowed. What's against the rules here is to go from a a constant, fa, into a universal x to fx. So this is an important feature here. You cannot go from a constant to generalize to a universal, right? Why? Because this basically is saying that I have one particular thing, right? Remember our example here was we had, Hegel is a philosopher, right? Well, if all I know is that Hegel is a philosopher, that doesn't necessarily mean that I know anything about all philosophers in general, right? I can't quantify that into a universal claim, right? So that means you're not allowed to do this generalization, but you are allowed to do this generalization. And what that means is it means that when you choose, when you instantiate, oftentimes you're going to want to instantiate into a variable if you know that eventually you have to generalize back into a variable, right? So here are some restrictions we should mention. And all of this is located in your book, and so you can take a look at that. There are two major restrictions, right? And I'm not going to write them all out because they're fairly long. I'm just going to read them to you, right? Right? Universal generalization may not be used within the scope of an indented sequence if the instantial variable occurs free in the first line of that sequence. Okay? And this is only related to the conditional and indirect proof, which we're going to talk about. So in a later video, so I'm not going to spend too much time on that, but it's worth mentioning now. There's a restriction that concerns the conditional and the inconditional. I'm sorry, not the conditional and the indirect proof. Right? And so we're not going to spend too much time on that now because you'll notice that in these sets of problems, we're not going to talk about that. We'll have a whole video just talking about the conditional indirect proof, right? And then also there's another restriction in terms of overlapping quantifiers. Right? And it says that universal generalization must not be used if an fy contains an existential name and y is free in the line where that name is introduced. Okay, so don't worry too much about these restrictions. We'll come back to them later, but there are restrictions on these. Right? In general, all I want you to do is see that if you have this, you can move to this, but you cannot do this. Right? This is not allowed. Okay, so let me do an example problem here for you, using the universal generalization so you can see how it works. And let's imagine we have this problem. All psychiatrists are doctors, and all doctors are college graduates. Therefore, all psychiatrists are college graduates, right? And literally, if we wrote out the problem, it would look like this, right? X to px, then dx. Also, right? If there's an x in the universe, anything in the universe that is an x, if that x is a p, then that x will be a d. If it's a psychiatrist, then it'll be a doctor. And then number 2 here, we have x dx to cx, right? If there's any x in the universe, if that x is a doctor, then that x is a college graduate. Therefore, right, if px, then dx. Right, now this looks like a good example of utilizing a hypothetical syllogism, right? Because I have a dx here. So it seems like I should be able just to say this, but here's the problem, is the hypothetical syllogism doesn't work when you have a bound statement function. Since these things are bounded by the quantifiers, this isn't going to work. So you can see here what we have to do is we have to instantiate. Now, so you can see here, since my conclusion is actually quantified, and I have this restriction here, that means that when I choose to instantiate, right, because remember, here was the instantiation rule, I could instantiate to a constant, but I don't want to, because if I instantiate to a constant, I can't re-generalize. So that means I'm going to want to instantiate to a variable, okay? So line 3 here, we have to actually instantiate both of these first, okay? So that means we're going to end up with p, and I'm just going to choose, I'm going to stick with x. It doesn't matter what variable I use, right? Px to dx, and this is going to be line 1, universal instantiation, and then there's going to be dx to cx, line 2, universal instantiation. Now that I've instantiated it, and you can see here I've freed up, I've opened up my conditional, the hypothetical syllogism, p then q, q then r, right? Therefore p then r, right? Notice, right, this thing is open and free, and now this is open and free. I can now utilize the hypothetical syllogism in line 5 and say If I have px, then I must have cx. Okay, so that's lines 3 and 4, hypothetical syllogism. Okay, but you can see here my conclusion is this, and I want to prove this. So this is where I can use the generalization rule. Because I chose to instantiate utilizing a variable, I can now regeneralize into the variable. So that means I can go x, and again, I'm going to, the rule applies to the whole line. So that means I'm going to go x to px, then cx, right? And that's line 5, universal generalization, okay? And that's how you would do this proof sequence, right? But you can see here, if I instantiated with an A or something, right, I could still do the hypothetical syllogism, but then I can't instantiate to a universal, right? We'll see later that I could instantiate to an existential, but that wasn't my conclusion, okay? So that's how we do that sort of problem there, right? Again, universal generalization doesn't apply to constants, only to variables. Okay, let's look here to number 3, our third rule here. And this is going to be the existential generalization. The existential generalization, this is EG for short. Okay, the existential generalization. Existential generalization looks like this, and at least in terms of, here's the definition. If I have FA, right, so if I have a statement function, I'm sorry, not a statement function, but if I have a basic, any sort of predicate claim, right, any predicate proposition that's not quantified, I can existentially quantify it, right, into this, right, to fx. So I can move from the constant into the variable, but I can only do it when I do an existential claim, because really this says that there's at least one that exists, and of course we know it's this one right here, right? So I can do that. Here's the other thing. If I have fy, right, so if I have an unbounded statement, but it's utilizing a variable there in that subject position, I can existentially instantiate it as well into x of fx, right? So existential generalization lets me take anything, basically any statement, and basically existentially generalize it, right? And that's pretty basic, and there's not really too many rules. There's no rules that you should worry about here, right? At least none that I can think of at the moment. Of course, yeah. So let's go here. So let's do an example problem. Let's imagine I had this problem. All clowns are scary persons. Jose is a clown, therefore there's at least one scary person in the world, right? So what would that look like? If I said all clowns are scary, that's going to be x, cx to sx. My second line here is going to be Jose is a clown, right? So if Jose is a clown, and the conclusion I'm looking for here is, therefore there's at least one scary person in the world, ex, sx. Right? I don't need the parentheses again because this applies to whatever follows immediately afterwards. So you can see here, well, how can I do this problem? Well, the first thing I have to do is, since I have a universal quantifier, is I need to get rid of that thing. So I need to do a universal instantiation here, right? And the question is, what should I instantiate it to? Well, since I see that there's a j here, I should instantiate it to the j, right? Because otherwise the problem's not going to work. So this is going to turn into Cj, then Sj, right? And that's line 1, universal instantiation. Remember, the universal instantiation allows me to pick whatever constant I want. And since I know that I need this in order to make the problem work, the modus ponens work, that's what I got to do. So line 4 here is, once I have this is a clear modus ponens. So this is going to be Sj, line 2 and 3 modus ponens. Right? Now that I've unlocked the Sj, I need to regeneralize, and this, of course, is our rule. Go back up here, remind ourselves of the rule. Excuse me. So I need to generalize. Now I have an Sj, so I have a constant here, but it allows me to go here to fx. And since the conclusion is an x here, obviously I want to choose that as my variable to generalize. So line 5 is pretty simple. It's going to be ex to Sx. That's line 4. existential generalization. Okay, and why does this work? It means because if I say that Jose is a scary person, right? That means that there's at least some people in the world who are scary, and that's what this statement says. This says some people are scary, really. Um, and so that's what allows us to do this problem. So we need to do a universal generalization in order to allow us to use our rules of implication. I'm sorry, inference or implication. By the way, I've just been using those terms synonymously. You don't have to. There's a difference, perhaps, but I've just been using them synonymously. And then once here, then I use my existential generalization here. Okay, and so that's how we do that problem. Now I've saved the hardest one for last, and that's the existential instantiation. And this is my EI, right? So EI. So let me write up here what the EI is. The EI, remember, if you're going to instantiate, that means that you're going to remove the existential quantifier instead of adding it, okay? So let's imagine the rule looks like this. EX, FX, so if you have any existential, right, statement function, you can move it into a constant. Now, here's an important thing. This is going to be called a statement name. I'm sorry, wait, did I have that right? I'm sorry, not a statement name. I thought I got that wrong. An existential name. This is an existential name. Now, there's an important rule about the existential name we'll come to here. Well, let's just do it right now. What's the basic rule? The rule is this. Anytime you do an existential instantiation and you introduce a new existential name, the name must be new. The name must be new, meaning it's not used in a previous line. Right? So it's not used in a previous line, right? And why is that? That's because the existential name is purely mechanical, right? It's just, we're just saying, we're just giving it a name to give it a name, but it's purely mechanical, meaning that we're not saying that it is a real thing, in essence. So that means that it can't be something that's already been spoken of in an earlier part of the proof, right? So it has to be a new sequence, and here's the other thing, it can't be in the conclusion. So you can't choose a name that's in the conclusion because it's mechanical, right? You're trying to prove things that really are true and are true. And since this is a mechanical device, it doesn't work like that, okay? So it can't occur earlier in the proof sequence, and it can't be a name that's used in the conclusion, right? It can't be a constant that's in the conclusion. So that's an important feature here. So I can move from EXFX into FA, but anytime I do this existential instantiation, I have to be highly aware of this rule that it has to be a new name and it can't be in the conclusion, right? And here's what's not allowed, right? What's not allowed, right? If I have EXFX, I cannot go to an FY. I can't use a statement variable. Why? Because remember, if I'm instantiating it, I'm trying to demonstrate the particular claim with something that's real, particular, right? An actual. Now, it's a mechanical actual, but it has to be an actual. But remember, a variable refers to anything in the universe, which means that you can't do this in instantiation. This is against the rules, strictly speaking. So whenever you instantiate, you always and only are going to instantiate to a specific rule. So let's give an example here. Let's sort of do a problem here and see if it works for you. Okay? Let's do this problem here, right? Oops. Right. Here's the basic problem if I was going to read it to you. All attorneys are college graduates, Some attorneys are golfers, therefore some golfers are college graduates. So what would that problem look like? It would look like this. X, right? All attorneys are college graduates, right? Line 2 is that some attorneys are golfers, right? Therefore, some golfers are college graduates, right? And so this is what the problem looks like. Now, how do we do this problem? What should we do? Right? Now, remember our rule. We have to do, obviously here, we're going to have to do a universal generalization. But remember, when you do a universal generalization, we can generalize either to a variable or to a name, right? Or to a constant, rather. And over here in this problem, we have to obviously do an existential instantiation in order to do this problem. But you can see the difficulty here is that if we're going to do an existential instantiation, our rule was we have to give a new name, a name that hasn't, a constant that hasn't been used at any point earlier in the sequence, which means which one should I do first? The answer is, since obviously I want to talk about the same types of attorneys, right? What I need to do is I need to make sure that I need to make sure that I do my existential instantiation first. And that's a good rule of thumb, right? Do your EIs first, right? That otherwise it won't work, right? So let's instantiate line 2 first, and let's give it a name. Let's use the D here as David, for instance. So we'll get AD and GD, right? And that's going to be line 2, existential instantiation. Now, because I use this mechanical device D here to stand for David, it's just a mechanical device, right? Sort of stand in, if you will, a name of something that would be an attorney, right? But now that I've used this, now I can do my generalization. And of course, I want to generalize not to a variable in this case, but to a constant, right? So that means I'm going to go A, D, then C, D, where I just switched out these X's with the D. Because I introduced this first, I can use the D here, and it's going to work out for me. So this is line 1, universal instantiation. Right? Now you can see here I just need to simplify, right? AD. And these are all the basic rules of inference that we've touched on before. So that's going to be line 3, simplification. And since I've simplified it, I can now utilize modus ponens, which is going to give me CD, right? That's lines 4 and 5, modus ponens, right? Now I'm going to commutate this and simplify the same one too. So that's going to be line 7. Because remember, my goal here is to get GX and CX. So I need to get the G and the C by themselves. Well, if I can simplify to this, I could just conjoin these two or use a conjunction together. So that means I'm going to commutate to GD and AD. That's line 3, commutation. And then line 8 is going to be simplification to GD. Line 7, simplification. Now that I've simplified, I want to conjoin these two things together because my goal is to make it look something like this, right? So that's going to be line 9. Here is going to be GD and CD. And that's lines 6 and 8, conjunction. Right? Now that I've conjoined these together, now I need to do my existential generalization, right? Remember here, where we have the existential generalization rule. Here's the existential generalization rule. I could have a constant or a variable, a variable or a constant. In this case, I have a constant, a D, which means I can now switch these out and add my existential quantifier, right? So that means I'm going to get line 10 here is going to be EX. Now remember, I have to do the entire line, so that's going to be GX and CX. That's line 9, existential generalization. Okay? Okay, and that was my conclusion here. So this is what the proof sequence looks like. Let me make it just a little bit smaller for you. Oops. So there you can see what that looks like now from a fuller perspective. We'll erase that, okay? So you can see here what was really critical is to realize to do my existential instantiation first, because this name here, this D here, can only be used for the first time once I introduce it. Okay. Now, what does that mean then? Here's a couple things to remember as well. As remember the rules for the existential instantiation. You can never instantiate a negation for the existential or the universal. Why? Because you can't show an instance of something that doesn't exist. It doesn't make any sense, right? And the other basic rule here is that whenever you do an existential instantiation, you have to introduce a existential name, and that name has to be used for the very first time. Okay, and then there were the other two sort of restrictions, but we'll come to those later, and those had to do with the universal generalization. So we'll sort of come to those later. So here, let's do a couple problems here just to show how this would work. And you can see here that there are actual multiple ways of doing these sorts of problems. So let me do actually a problem from your homework just so I can show you how it's done. And this is from 8.2 Rules of Inference. So let's just go back down here. And I encourage you to read this all very slowly. Make sure to read this, right? Here they do other problems. excuse me. Right, so here's the rule, right? You can see this is invalid. Why was this one invalid? Right? Why was this invalid? Oh, I'm sorry. Let's see here. Oh, well, we'd have to read here. I'm not sure why it's invalid, but without just looking at it here, my mind's racing around here. But take a look at this chapter. Sorry, I meant to get you on the homework here. Here's a number of problems you can take a look at. It's really not difficult. Once you get the hang of utilizing this, it's just another tool we can utilize. So let's do a problem here. Let's do number 3. Let's do this problem here. Okay. Alright, now this one's a good one here because we've got a number of things going on here, right? You can see here I have negations and this sort of thing. This seems to be problematic, right? Well, always, again, like always, start with the conclusion. And the conclusion is I want this AX, right? EX here. So I need to get this by itself, which means I'm going to need to get a negation AX at some point to generalize. I can't instantiate a negation, but I can generalize one. So line 3 here is the first thing I need to do, obviously, is do a universal instantiation for this. You can see my goal is going to be an existential. So that means I'm going to pick a name. Obviously, let's use BM here, okay? So line 3 here is going to be AM to BM, right? And that's line 1, universal instantiation. And since it's a universal instantiation, I chose a constant this time because line 2 tells me I need a constant in order to make it work. If you will, think about it like this. You need a common denominator, and that's sort of, you have to figure out whether or not your common denominator is going to be a variable or a constant. Okay? Now that I have this, of course, I can utilize modus tollens. That means if I don't have BM, I must not have AM. So that's negation AM, right? And that's lines 2 and 3, modus tollens. So if I don't have this, now we can do our generalization, which means I'm going to generalize the entire line. So that's going to be EX negation AX, where I change out the constant and put in the variable instead because now I have a quantifier, an existential quantifier. So that's line 4, existential generalization. Oh, I'm doing the backwards, aren't I? Existential generalization, my egg, okay? And so you can see that problem's not too difficult. What maybe threw people off would be this negation, but remember, you can generalize a negation, you just can't instantiate a negation, right? You can't instantiate a negation. That should make sense too, right? If I say that a particular unicorn doesn't exist, right? Well, I can universalize that to make a categorical claim that the particular doesn't exist, right? Okay, so let's do one more problem because that was actually pretty easy, not too difficult. So let's sort of scroll down here. Ooh, let's do number 9. I bet number 9 is a difficult problem. And again, I haven't done these problems ahead of time, so let's hope I'm able to do them. Okay, so let's start with this problem. Okay, you can see here my conclusion is going to be BM or BN. Notice I have 2 different names here that are going to have to be conjoined. You can see here I could utilize the rule of addition and just add this potentially. But of course, the first thing I need to get this thing, well, you can see I have AM or AN, right? So how am I going to do this problem? AX to BX. What can I do here? Well, line 3, it seems like the first thing I have to do is I have to instantiate, do a universal instantiation for this. So the question is, what should I instantiate it to? What should I instantiate it to? Well, you can see I should probably instantiate it to M. And guess what? I could instantiate it twice to do N as well, and I think that's probably what I'm going to have to do. So, but let's do our first instantiation. It's going to be AX to, oops, I'm sorry, AM. Dang it. Sorry about that. Let me erase. Okay, let's try that again. So line 3 here is going to be AM to BM. Notice I had, since I instantiated, I have to choose a variable that's the same for both of these. So that's line 1, universal instantiation, right? Now, what about this N? Don't you think I need this N thing too? Well, it looks like I do too. So let's do line 4. I can instantiate line 1 again, except this time instead of using the M, let's use an N. So that's going to be AN to BN, right? And that's line 1, universal instantiation. I can instantiate it as much as I want, actually. Because remember, if it's a universal, all I'm doing by giving it a constant is just giving a name to a particular member of the category. There could be many, many categories, many members of that category, right? And so that's what I'm going to do, is I'm going to choose those two names. Now that I've got these together, it looks like I should conjoin them, right? So let's see, which way should I conjoin them? I should start with this one, line 3. So I'm going to get AM, then BM, and AN, then BN, right? And that's lines 3 and 4 conjunction. And so since I've conjoined these, and now look at line 2, I have a constructive dilemma set up, right? Because this is saying if I have either this or this, then I must have either this or this. So line 6 here is going to be BM or BN, and that's lines 5 and 2, constructive dilemma. We'll put CD for constructive dilemma, okay? And that, of course, is my conclusion, so that's the proof. So you can see all I had to do, the difficult part of this one is knowing that you could instantiate it twice. So I'm actually glad I did this problem for you, so you could see how we do that problem. We're at 42 minutes. I think we have time for one last problem here from the homework sequence here. Let's do... These are translation problems. I'm not going to focus too much on translation problems, mainly because most of the time I really want you to learn the mechanics of doing the symbolic work. I'm not one to be as worried with those other problems. Let's do problem 12, right? Okay, let's take a look at this problem. So, okay, you can see here I have, okay, I have an AX, and I have, this here is an existential, this is an existential, right? I'll just put an E, and this is a universal, and I have a conditional. So that means that if I could get this by itself, I could get this by itself. My goal is CM. You can see the CM is right here. So what do I got to do here? What am I going to have to do? Well, the first thing I need to do probably is get one of these things by itself. So, and that's going to be an AM. So let's do line 3. Let's just put AM by itself, which means we're going to simplify line 2. So that's line 2, simplification. Now that I've simplified it, now let's do an existential generalization, which would allow us to do this problem, right? So let's existentially generalize this. So that's going to be line 4. And again, let's see here if I can show us the rules. Okay, this is sort of a mess. You probably can't really see this too well. Okay, so remember here, for the existential generalization, right, if I have an FA, I can always go to it, right? Or if I have a variable, I can do either one. So, but I'm going to use this one right here. So let's go back. So that means AM is going to turn into EX, AX, right? And that's line 3, existential generalization. Now that I've generalized this, I have this. This is my PQ sequence in a modus ponens. And the reason that I can use modus ponens here is because the conditional here is not bounded by any quantifier. So that means line 5 here is going to be x, bx, then cx, right? And that's lines 1 and 4, modus ponens, right? Now remember, my goal is Cm, right? So what I need to do here is I'm going to need to do a universal generalization. I'm sorry, universal instantiation here. So line 6 here is going to be B, and here I'm going to use a constant. I'm going to use M. Remember, for the universal instantiation, let's find this. The universal instantiation, I can either go from a constant to a from a variable to a constant, or from a variable to a variable. In this particular problem, it would be the wise thing to use a constant, and I'm going to use the m as my constant. So this is going to be bm, then cm. So I've now existentially universal instantiation, line 5. Sorry, my handwriting's a little bad. So now that I have this, notice up here, line 2, where did my thing go? Line 2 is, I just need to commutate and simplify this. So let's commutate this. You know what? I'm running out of space on this problem. That's all right. So that's going to be bm and am. That's line 2, commutation. I just needed to switch these two things around. So line 8 here is going to simplify to just bm. So now that I've simplified to bm, that's line 7, simplification. You can see here, I'll write line 9 up here. Since I have this, and I had the bm, then cm, I can conclude cm utilizing lines 8 and 6, or let's go 6 and 8, modus ponens. Okay? And that was how we completed this problem here. Okay? So that wasn't really too difficult. The trick here was to recognize that you could use modus ponens on line 1, right? Okay, so let's do one more problem here, because I wanted to do one problem where we had to do an existential instantiation, so that you can see how that works. So let's see if we can get a good problem here. Here, I have a problem here in my notes here that we'll use. That'll be a good example for us. Because I don't know off the top of my head which homework problem in the book utilizes an existential name. But let's just give one here, this problem here. Let's imagine I had x, ax, or bx, then cx. Line 2 was ex, ax. And the conclusion I'm looking for here is an existential CX, okay? So how should I do this problem, right? Well, you can see here I'm going to have to do a universal I'm going to have to do a universal instantiation at some point, and I'm going to have to do a am I missing a parentheses? Oh, I am. I'm missing a bracket. Okay. So, and I'm going to have to do an existential one too. Obviously, if I do an existential instantiation, I can only choose a name. So it has to be the first line, so I should do this one first. So let's do that. So let's just choose AK. Right, and that's going to be line 2, existential instantiation. And now let's do a universal instantiation to the constant of K. So that's going to be AK or BK, then CK. Notice since I'm instantiating the same thing, I have to do a K for each one of these. So then I get these Ks, right? And that's going to be line 1, universal instantiation. Now that I've done that, line 6, I can obviously just add BK to line 3, AK or BK. That's line 3 addition. Now that I have this, I can do a modus ponens to CK. That's going to be CK. Right, because notice these two things are identical. So I can use the modus ponens to unlock this, CK. So that's 4 and 6 modus ponens. Now that I have this, I just need to do an existential generalization to the x. Pretty simple, actually. EX to CX. And that's line 7, existential generalization. Okay, so that wasn't a very tricky problem. There are ones that are much more trickier than that. But that's basically how you do these problems, okay? So I hope that explains this. And again, the real trick here is ultimately to sort of have fun with doing this. And I know that the real trick is to change your mindset in terms of thinking of this whole process as very difficult and hard to wrap your mind around. And instead, think of this as logical puzzles and think of this as fun, because if you can think of this as a game, you're going to do well. And some of the people have written me back and said they're starting to have fun with this, which is what I'm really glad to hear. Because I'll tell you what, every time I teach this logic course, when I get to this part, a lot of times, I'll just be sitting home by myself and just running through some problems, some proofs, because I actually think they're actually very enjoyable. They're puzzles. So think like approach the problem like they're puzzles. Have fun, most importantly, and you'll find that they're not as difficult as they seem. Okay, I'll see you guys online. In our next lesson here, we're going to talk about the change of quantifier rule, I believe, which is going to we're going to be able to talk about what happens if you have negations and stuff like that. How can you instantiate stuff like that, and what can you do? And the change of quantifier rule is going to allow us to do this. So anyway, I'll see you guys online. Thanks for watching. Okay, bye.